first two questions here, we're going to need to be rearranging the conditional probability formula. What the conditional probability formula tells us is that P of A given B equals P of A and B over P of B. Notice in this version of the formula, after the given line was B. If we switched it around and instead tried to find P of B given A, what would change is that the bottom would now be P of A. The top of the formula is still the probability that both occur at the same time. So really, what the first version is saying is, we know B already occurred, what's the probability that A occurs? Since we know B already occurred, it's only out of the probability of B that things can happen. What goes on top is when A also occurs with B. That gives us the overall probability that if we know B occurred, what's the chance that A occurs? So here's how we're going to use this. Basically, we've been given this, we've been given this. This is our unknown. So we're going to plug in the two things we know and solve back for our unknown. In question 1, they told us P of A equals 0.9, P of B equals 0.8, and P of A given B equals 0.75. One of these pieces of information is unnecessary. Specifically, P of A does not factor into our formula. It would if it was B given A, but since B comes after the given line, we only need to know P of B here. So they've told us P of A given B equals 0.75. We're trying to solve for P of A and B. We know that P of B is 0.8. So all we need to do now is multiply the bottom here, 0.8, times the left side, 0.75, and that'll leave us with P of A and B. So P of A and B equals 0.8 times 0.75, which gives us a final answer of 0.6. For question 2, it's the same setup, just switched what we're conditioning on. So now, because after the given line is A, P of A is the one that we need, we'll no longer need P of B. So we set up our formula, P of B given A, which was given to us as 0.5, equals this unknown P of A intersect B, divided by, in this case, P of A, which is 0.9. Again, we're solving for this unknown. To do that, we'll multiply both sides by 0.9 to get rid of the divide by 0.9 here. So P of A intersect B is going to become 0.5 times 0.9, which should give me 0.45. So again, with these types of questions, we're really using the general conditional formula and just rearranging it. That rearranged formula that's already solved for P of A and B is given to you in the PowerPoint lecture, but personally I prefer just to know this one formula and rearrange it algebraically. The next set of questions is based off of this table. This table is given to us in proportion form again. The difference is, instead of just picking out specific cells, we're going to need to know how to do conditionals with this table. Like before, my preference is that we start by adding all the rows and columns so that we have those totals to begin with. First column, 0.28 plus 0.02 gives me 0.30. 0.27 plus 0.23 gives me 0.50, and 0.11 plus 0.09 gives me 0.20. When I go across, 0.28 plus 0.27 is 0.55, plus 0.11 is 0.66. 0.02 plus 0.23 is 0.25, 0.25 plus 0.09 is 0.34. Either way I add it, 0.3 plus 0.5 plus 0.2, or 0.66 plus 0.34, should give me 1, which tells me that these do add up correctly. Now that I've got everything laid out like that, it's time to find my conditional probabilities. Always with a conditional, you want to understand that the given line, this line in the middle of the probabilities, separates what already has happened from what we want to see what the probability now is of happening. So, for this first one, we already know that the student was on time. What that means is we can ignore any part of the table where the student was not on time. So basically, we're limiting ourselves just to this first row of the table. This first row represents students who were on time. We already know that the person was on time. So the total of this top row is 0.66. That's going to be the denominator of our equation. Within that row, anything that fits what's in front of the given line goes on top of the equation. So live on campus is this first cell. We're only counting the in time row live on campus. We're not counting the ones who are late. So that's 0.28. We can now put this division into the calculator to find out the overall probability. When I do 0.28 divided by 0.66, I get 0.424. I'm going to call it 0.42. Next question says, what's the probability this student lives on campus given that they were late to class? So the thing we know is that they were late to class. Here's the late to class row. It's out of 0.34. When we then look within that row for the specific cell where the person lived on campus and were late, that's this 0.02. When I put in my calculator 0.02 divided by 0.34, it tells me 0.0588, which I'm going to call 0.06 when I round. Again, I don't really care about you rounding on these. It's fine to give me more decimals. I would say be a little careful when you're doing them in centigrade, just in case they tell you to go to a specific number of decimal places. For number 6, the probability of on time given live on campus. Here, after the given line is live on campus, so it's going to be isolating a column, not a row. Specifically, this live on campus column that's out of 0.30. Of them, the ones that were on time were 0.28. When I put that into my calculator, 0.28 divided by 0.30, I get an answer of 0.933 repeating, so I'm going to call that 0.93. Question 7 says, we know they drive to campus. What's the probability they're on time? Drive to campus is out of 0.50. The ones that are on time is 0.27. When I put this into my calculator, it tells me 0.54 is the probability. Question 8 says, we know they take the bus. What's the probability that they were on time? So of the students that take the bus, that's just this column, it's going to be out of 0.20. Within that column, the ones that were on time is 0.11. When I put in my calculator 0.11 divided by 0.20, I should get 0.55. Question 9 says, what's the probability that they took the bus given that they were late? Given that they were late means we're isolating this row that's out of 0.34. Within that row, the ones that took the bus are this 0.09. If I put in my calculator 0.09 divided by 0.34, that's how I get the answer of 0.264, which I'm going to call 0.26. Finally, question 10 asks me, what's the probability they take the bus given that they live on campus? So I start by isolating this column, live on campus. Within this column, live on campus, none of the students take the bus. Really, this is an example of a mutually exclusive situation. Students can only do one of these 3 things. If we know they live on campus, we know they don't drive to campus or take the bus. If we know they drive to campus, we know they don't live on campus or take the bus. So if you condition something on another column, and you ask what's the probability of this column given it's in this other column, 0 is the probability. These 2 columns are mutually exclusive. They cannot happen at the same time. Going along with that idea of mutual exclusivity, here in these problems we're told the probability of A occurring is 0.72, the probability of B occurring is 0.11, and importantly, A and B are mutually exclusive. What that needs to mean to you is that they cannot occur at the same time. If A and B cannot occur at the same time, then the probability that both things occur has to be 0. It's 0 because they can occur at the same time. When I now look at the probability of A union B, previously when we did unions and we were looking at A union B, we need to add together the total in the first set or the total of the row plus the total in the second set or the total of the column and subtract out the overlap. So it's really P of A plus P of B minus their intersection. You're subtracting the intersection because otherwise they'd be double counted. In this case, the intersection is 0, so I don't have to worry about subtracting it. I can simply take 0.72 plus 0.11 and get 0.83, knowing that there was no overlap and there's no need to subtract out from that. For questions 13 and 14, they're a lot like question 10 here. If we know B already occurred, and if A and B never occur together, then there's a 0% chance that A occurred if we know B already occurred. Think of it as something like, you know that this person voted for President Trump in the 2016 election. It's impossible that they also voted for Hillary Clinton. So given that they voted for Trump, what's the probability that they voted for Clinton? 0%. Similarly, if we put it the other way, given they voted for Clinton, what's the probability they voted for Trump? Again, 0. Two mutually exclusive events have a union where you can just add them, but they have no intersection, and regardless of which way it's conditioned, 0 is the probability of one happening given that the other occurred.